introduction. And it's my great honor and a pleasure to give a talk in this wonderful event. And I so appreciate Professor Yao, who gave such a desirable opportunity for us to get together to work on interesting topic. And I'm so moved because it's not easy to get such a good opportunity to do so. And but just Professor Yao provide such a help and support. My talk today will on statistical foundation of artificial intelligence. Some years ago, the artificial intelligence may be considered as a science fiction, but today it is not. It is real. It is here now. It will stay with us forever in science and society. More importantly, AI is profoundly revolutionary our way to understand the world and to change the world. Now, AI is take off. As a statistician and a mathematician, what we need to do? AI has lots of utility, so save lots repetitive jobs and provide the profit and create the more creative jobs. But it also has some harm because, for example, he may provide some created some misinformation and may create the cyber warwares and also some amplify the bias. So how we can maximize the utility and minimum its harm? So we need to understand what is the foundational and fundamental form of AI, how AI works. So I would think this core is just the statistics. Statistics play an important role in promoting AI. This role can be liberated by mathematics. So, for example, if you write article by AI, so you can use a probability theory and to generate continuity of text based on a list of words. The fundamental kernel of how AI works is actually AI is a machine learning. By input and process data, so AI will generate outcome like classification and prediction. So this device is a neural network, deep neural network. So from one step to the next step, the data will be processed, will transform to the next stage. Each stage, depending on previous stage, so in each step, statistics play an important role. So you can see everywhere in these stages, there is a statistics. Currently, there are several approaches which have been used in AI. I list several of them here. I will introduce one by one, but some of them we have made some contribution. So in my opinion, the current statistics is too simple to capture the complexity of the big data. So we really need to develop more advanced statistics to capture the complexity of big data. So I will tell you where we need to develop statistics. Actually, if one say no AI without statistics, I would say no advanced AI without advanced statistics. So there is a great effort to develop advanced statistics by the many large language models like the open AI's GPT and Google's BERT and so on. So there lots of opportunity and lots of effort to develop statistics. Now, I like introduce each of these statistical approaches. The one highlighted in color has been developed in our team. The probability theory. So probability theory is that define some concept of random variables distributions. So and estimate that how likely event occur given the data. So for example, if you write an article called genetic architecture of stemwood growth in forest tree, given the data set trained by a large language model. So AI will help you produce the article. This process is exactly based on probability theory. So there are lots to do. There are lots of steps in the probability to help you to write the article. The regression model. Regression model is the technology which estimates the relationship between the dependent variable and the independent variable. So the regression can be used to prediction and estimation and explanation of various phenomena. So current approach for linear regression is linear. Is linear. But in reality, the nonlinear relationship is more common, more important. So the current approach is just a linear regression model. So for example, we have data like this. We have data, A sample, collect P variables, P independent variable, and one dependent variable, Y. So we generate the model. Let's see, should be this one. So we generate the linear model like this, Y equal B0 plus B1 x1 and B2 x2 and so on and so forth. So you can see the multi-linear regression model. So this square have been used to estimate the parameters B0, B1, and so on. And because we have so many variables, so the variable may highly correlated. In some situation, P is larger than N, the typo. So P should be is larger than N. In this case, so we need to perform variable selection. There are several approaches which can be used to for variable selection, ridge regression, and lasso, and some variety like adaptive and group lasso and static net. So those approaches basically do same things, but based on different criteria. So as I pointed earlier, linear regression is too simple to capture the nature. So we really need to develop a non-linear regression. So based on the same data, so we develop approach to estimate the nonlinear regression model. To do that, we need to integrate some knowledge from other disciplines, like ecology. So in ecology, there is a concept called niche. The niche is total environment of a species which are living in a habitat. So we, for example, according to this concept, we can suppose one sample, for example, here, first one sample is the community is a complex system which include variable y and x, px. So this component may interact with each other to determine this whole system. So based on this, the linked concept, we can take the value of all these variables, take sum actually. So you may ask me if how happen if we have different scale, for example, the height, the weight, the different scale, how we can take the sum for the different scale. To do that, actually, we first rescale this data. So make the variable with different scale comparable with each other. So in statistics, the rescale is commonly used. We take the rescale the value, take the value for this. We call this sum of all these variables as the subject index. Do same things. We can calculate the variable index for this one. So you can see each variable here now has a relationship with the subject like part and whole relationship. So part and whole relationship follow physical law like this. A cubic, the surface area of a cubic always proportional, positively proportional to its volume. That's a physical law. So you may not ask me why. So physical, that's the first principle. So right. So actually, this relationship is also common in nature. So this butterfly body weight and butterfly wing length is follow such a relationship. This relationship can be modeled by power equations. So why power equation can capture such a part-whole relationship? In 1997, West and Brown and Inquest, these three people worked together using the biophysical principle to explain why power equation can describe the part and whole relationship. So you can see this is a physical law, and later on, people explain why this physical law is true in nature. So use this idea. So we can do similar things. So we can model the variable as a function, as subject, using the power equation like this. So surprisingly, by analyzing real data, is the gene expression data, we do find such a fitness, very good fitness by power equation. That is individual expression. That is the total expression, subject index. So you can see the fit is very well. Okay. And so later on, we need to incorporate one big idea, game theory, to model how variables interact with each other. So in my opinion, the variables interact with each other just like two cats try to compete or cooperate with each other. So if the two cats are similar in size, they may tend to be collaborate. If one is smaller, larger one is larger. Larger one may compete, will fight against the smaller because it feels it's easier to get more resources from smaller the cat. So this competition and collaboration determine game theory. So lots of people have worked in this area. So and John Nash provide Nash equilibrium, which make the game theory more practically useful in economic study. In the 1970s, the Merritt Smith and his students integrate game theory and evolutionary biology to create a new discipline called evolutionary game theory. So this theory can used in everywhere, which may not depend on the rationality assumption. So just like game theory actually is a dynamic process. For example, so left cat choose cooperation, the right may cooperate, the two cooperate. The one is try to fight, the second one also can fight. And so on, they may change the pattern of fight. And this so you can see this is a dynamic process. So we may calculate the niche index for each event like this, and based on the idea from the ecology community, so we can generate such different equations. So the first the pair of first cat is dependent on the strategy itself, and also the strategy from other cat. Same things for second cat. So you can see this differentiation includes two parts. The first part in yellow is called independent component. Just the self-regulation is only dependent on the self. And the second part in purple is dependent component, which is inference from other alternative cat. So I call dependent component. So I call this model is a mixed the different equations. Okay. This model looks like similar to LV model. The LV watery, the two ecologists developed LV model. So LV model has a beautiful mathematical parameters. But our model is similar but different from this model. So which also has very beautiful the mathematical parameters proved by my collaborator Chris Griffin, who is a mathematician. So he very delighted to see the model I developed. He immediately gave some proof for the mathematical the parameters. So you can see right here. So we can how we can transform the linear regression to the nonlinear. So right here, so unknown linear form, and these two parts were unknown linear form, but we fit by power equation got this nonlinear, and we to do that to fit this term, we incorporate non-parametric legendre orthogonal polymorphism, LOP. So after LOP transformation, this linear form become the nonlinear form become linear. Okay, that's very nice. And if this is linear, so we can easily take a integrate. So this difference derivative becomes the actual value. So you can see now, based on this linear form, we can use variable selection. So variable selection has largely based on linear regression. There are no very good approach yet to the nonlinear regression. But right here, we develop a nonlinear regression model, which is more biologically true in nature. But after transformation, LOP transformation, we can convert nonlinear form to linear form. On the linear form, so we can easily manipulate by variable selection. So that is, I think, is in statistics is very good the progress advance. So, and with this, so you can see that multi-linear regression of nonlinear dynamic system. So we can get this, we can use lasso to select the subset of the most significant variable which are linked to Y. So, so you don't need to include everything, but you just select the most important X to Y. That is statistically reasonable and also needed. Okay. And the good thing is also overcome the issue P large, much larger N for nonlinear complex system. I think that's very good statistical advance. So I use the model to analyze true data. So the tree, so you cut the tree, measure the range, length, and the height, and you can see the height follow the curve like this. And the statistical is independent component. This one is a dependent component, which means that diameter growth negatively affect height growth. But right here, height promote the diameter growth. So this stem diameter growth and the stem height growth are very important process for tree growth. But these two processes has some competition or cooperation. The model we developed can beautifully identify which, in which case they compete, in which case they cooperate with each other. Third, the topic is about classification model. So actually, we do not do much in this area. I may skip quickly. The fourth, the clustering model. So we cluster is very important in AI. So we have big data. So how we can analyze high dimension data? The first thing is make a dimension reduction. The cluster approach is one of the important approach for dimension reduction. So current approach is widely based on K-means, which is very limited, at least the limitation right here. So actually, is most important limitation is still linear, based on correlation among P variables. The correlation is a linear the measure of relationship. And also the no mechanistic principle is implemented for the K-means. So to overcome this limitation, we propose a power tool by incorporate power law. Go back to this data set, same data set. So we can incorporate the mixture model. In statistics, there is a mixture model like this. P variable supposedly have L cluster. Each cluster has a proportion pi. And the mean has a distribution, normal distribution like this. With distribution has a mean vector. This, you can see the mean vector finally fit by power equation. And also the n by n covariance, should be P by P covariance matrix. these variables follow some structure. So we have some state product to fit the structure of the covariance. Okay. So and with this, so next we may just incorporate the algorithm to estimate the parameters. This approach is called hybrid EM algorithm and a simplex algorithm. So in each step, we calculate the posterior probability, and the M step estimate the parameters. There are three parameters: proportion and the power coefficient, and the parameter which model covariance structures. The three type of parameters we need to estimate in this algorithm, by this algorithm. Actually, the algorithm is hybrid, so integrate EM and simplex. So this here is an example. So we have several thousand genes, maybe over 10,000 genes. We will cluster different groups. Each group has many different genes. So you can see the curve looks different from cluster, between clusters. Okay. So functional, there's a functional cluster can cluster different the variable into different groups, right? Into different group. Each group similarly has a similarity in the function. But we can do other way around. We can cluster samples. We have n samples. Cluster n samples into different categories. If you do this, which is exactly what we want to do in precision medicine. In current medicine, so we want to take a drug individually based on the genetic background and the lifestyle. So everybody, not everyone take the same drug, but we take a different drug for different people. How we can do that? So we need a cluster those people into different groups. Each group has similarity in the genetic background, genetic information, and so on and so forth. So we can use same drug for same group. So this final cluster can do same thing, can play important role in precision medicine, besides the drug. Okay, so we just do some comparison right here. Yeah, so K-means is currently used in AI. So the AI is currently widely used. So it's a very have many limitations. First is the linearity and the correlation based on correlation of distance, and is a phenomenal observation and statistical, just test the statistical significance, but not incorporate the first principle. And so we can see the comparison between K-means and our approach. So this functional clustering has also a lot to do in graph theory. Okay, so we may divide a big graph into sub-different graphs based on functional clustering, which is different from top-down approach. Our approach is bottom-up, so it's alternative to the current approach. And fifth topic is a graphic model. So I'm very confident. So we did a lot of work in graphic models. So current graphic model mostly is based on probabilistic model. So you only can estimate the probability of a variable given the other variable. But we can estimate exactly the interaction, the stress, the sign, and the direction. So go back to this data again. So based on this, we can construct the key variable, how they connect with each other in a graph. So we can formulate a general model. The most important things here So we can generalize this model to include high-order interactions, not only just the pairwise. We can include high-order interactions. So this makes the model more generic. So can be used in a great practical scenario. So the most important thing here is how we define the interaction. So we use game theory and ecological theory to define the interaction term. This model has been used to test the gut microbe. Gut microbe has a lot to do with human health. So this Amish population is ideal population to study because the uniform, the genetically heterogeneity, and the living in the uniform environment made easier compare. So we detect some the interaction. Looks like very you can see you can see the different microbi interact with each other that has a very complex interconnected link. So include high order interaction. So we can identify which microbe is central, is a hub to determine the gut microbi. So this model can analyze any data, any dimension of data, not only just a couple variables, human variables. We can analyze several hundred variables, even several thousand, several millions variables, because we have our which is the functional clustering. So we can always cluster huge amount of variable into different group. So with this idea, you can handle any dimension of variable. So in the end, so you may see that the multi-layer and a multiplex and multi-functional network. So first the layer and the second layer and the bottom layer, which is record the information flow from one variable through different strengths to the other variable. So project the tri-dimensional geometry on the surface. So you can, just like river strengths, so you can see the information flow in this surface. So no matter how many variables for this model, we can handle the 1 million variables together. Okay, so in the deep learning model, we didn't do much yet. So I just skip quickly. So the last topic is topological statistics or statistical topology. So this one has been working with the Professor Jie Wu and guidance of Professor Yao. So Professor Yao recently developed path homology theory, which is called GLMY homology theory. So we incorporate this theory to the network construction to better understand information flow in network. So just like this, so we got we have big data, lots of data here, the messy data. But our model now can handle huge amount of data, so get the network. With the network, Professor Yao's theory can what to do, can get the topological structure. For we can see that how the spatially connected of each among different nodes found different variables. So we can clearly record the information flow from one node to other node through very different paths. Right. So this is a very powerful approach. We the most important things, we are not just speaking, but we do real things. So we have the example. The model we incorporate so the network meet GRM homology theory. So with by Professor Yao's work, and through Professor Jie Wu, as you know, he is very well-known topologist. He's very knowledgeable in algebra topology. So I learned a lot from him to get this thing together. So in example, so we got some very interesting findings. So because of time limit, I may skip, but I just jump to the most important slide. So jump this is the GRMY, the homology result. But I jump to last slide here. So based on GRM homology dissection, so we find very interesting things. So as you know, the IBD is an important disease, making you very painful, right? So to prevent your pain, doctor design a drug similar to histamine. Histamine can inhibit the disease, can inhibit it, so make you better, feel better. But actually, this not it's just the inhibit disease, but not eliminate disease. Just because actually there's some upstream right here. This one is very important. Need promote this guy. This guy promotes the histamine. Histamine inhibit disease. In the health control, this test is very universal. So everybody has such a pathway test. But in the UCD, these two are different type of IBD disease. So you can see for CD, this guy inhibit the